Welcome back everyone to another video in our Fundamentals of Structural Engineering course. In this video, we are going to learn about structural design of steel tension members and steel connections. For any steel tension member, there are three main failure modes. The first mode is yielding, and in this case, the failure happens in the steel section itself due to excessive tension force and due to reaching the yielding strength of the steel member. Second and third modes are rupture and block shear, and those failure modes happen in the bolted connection itself. Right now we are focusing on the yield failure. After that we will start learning the rupture and the block shear failure modes. For the yielding failure, this is very simple. We are governed only by the tensile force, so this is a governing equation for us, which is phi Tn has to be higher than or equal T ultimate, where Tn, which is the nominal tensile strength of the beam, could be calculated by this equation, which is area gross multiplied by F yield, where phi equals 0.9 for the steel tension member. Here we are using F yield directly because this is a tension member and we don't have to worry about any buckling or lateral torsion buckling or any of those which we have learned in the design of beams and design of columns. So let's have an example on this. Here we have a W2168 beam. This is the section name, made of A99 992 steel, which has a yield strength of 50 kSi. The surface loading on this beam results in a 240 kips tension due to uniform load live, and 160 kips due to tension load live also, and 45 kips tension load due to on weight, which is dead. What is most nearly the available beam's tension strength, and is the beam adequate? In order to solve this problem, we need to calculate first the T ultimate, which is the ultimate tension force, and after that we will calculate the design strength of the beam and we will compare both of them together. So in order to calculate the T ultimate, we know it equals 1.2 T due to dead load and plus 1.6 T due to live loads. So this is going to equal 1.2 multiplied by 45 plus 1.6 multiplied by 240 plus 160, which is going to equal 694 kips. Next step, we need to calculate Tn, which equals area steel multiplied by F yield. We can refer to the table 1.1, which has all the steel sections and their properties, and we will get the area, which is going to equal 20 inches square. So this means that Tn equals 20 multiplied by 50 equals 1000 kips, but we need to calculate the phi Tn. This is very important. Don't ever forget the reduction factor. So it is going to equal 0.9 multiplied by 1000 equals 900 kips. So this means that phi Tn is higher than T ultimate because T ultimate equals 694. So this means that the beam is adequate. So this is our answer, which is the first option here, 900 kips for the design strength of the beam, and the beam is adequate. Let's start learning our second failure mode, which is rupture mode. In this failure, as you can see here, the rupture or the failure is going to happen in the bolted connection itself. It can have any pattern of those patterns which you can see here, depending on which one is the weakest connection in your steel connection. As you can see, it could be just perpendicular, it could be staggered like this or staggered in different way. That's why we need to check this possibility. To check this failure again is rupture, we have this equation which is phi, this is for the steel, it equals 0.75, and Pn, which is the strength available for the connection, equals F ultimate multiplied by area effective. And area effective, it equals U multiplied by area net, where U is the shear lag factor. It normally equals 1, or we normally take it as 1, and most of the time it is given in the problem itself. But I'm going to have a separate short lecture for you explaining how to calculate exactly this shear lag factor, just in the rare occasion that it was not given for you in the problem. But for now, we will consider it as 1, while An is the area net, which is the area gross of the section minus the area of the bolts. And this is of course for the bolted connections, while area net equals area gross for case of welded connections. So how can we calculate the area net, which is the area gross minus the area bolts? In order to calculate the net area of any section, you can see here this is a tension member and we have this bolts holes here. This is the area which we want to calculate, this shaded part here, because this part is going to be drilled for the bolts. So in order to calculate this shaded area and in order to calculate this deduction part, we need to understand this. The bolts hole's nominal diameter equals the bolt's diameter plus 1/16 inch. This makes sense because if our bolt, for example, is 1 inch, there is no way that this hole is going to equal exactly 1 inch. There must be some kind of tolerance at each side of the hole. This is why if the bolt is 1 inch, this means that the nominal hole diameter is going to be 1 plus 1/16 inch. After that, we deduct another 1/16 inch for each bolt hole to compensate for any damage that is going to occur during the drilling. So here if dB equals the bolt diameter and dn is the hole's nominal diameter, in this case dn is going to equal dB plus 1/16, and in the calculation of the area net, it will be calculated based on this equation, which is this h, which is the height, minus sigma dn, which is the nominal diameter of the holes, plus 1/16. This 1/16 is for to compensate for any damage, and this dn itself, it equals the dB plus 1/16 for the tolerance. So in summary, we add to the bolt diameter 1/16 for the tolerance and another 1/16 for the damage. In case it is given for you in the problem directly the whole diameter, you add only 1/16. And of course all of this will be multiplied by the t, which is the thickness. So now let's have an example of this. Here we have a steel flat bar tension member, has a tensile yield strength of 50 ksi and the ultimate strength of 65 ksi. Holes for a bolted connection are punched at the end of the member. The effective hole diameter is 1 inch. This is the effective hole diameter. The net tensile area is most nearly, and we want to calculate this net tensile area. So this means that the area net equals h minus sigma d plus over 16 multiplied by t. Here the dn, which is the nominal hole diameter, is given directly as 1. So the area net is going to equal 8, which is the height, minus 2, because we have 2 holes here, multiplied by 1 plus 1/16, all multiplied by 0.5, which is the thickness of the web, and it is going to equal 2.94 inches square. So this is the answer here, which is the third option. Now we'll start learning our third and last failure mode, which is the block shear. In this failure mode, as you can see, a block of our member is going to be separated due to a combined effect of the shear stresses here and the tension stresses here. As you can see, if we will zoom in on this part here, this part here is under effect of shear, and this part here was under the effect of tension failure. So this failure mode is going to be checked using this equation here. We need to calculate the area gross for the shear, which is this area of this surface, and the area net for the shear, which is this area deducting this the area of the bolts, and the area net for tension, which is this area after deducting the area of half of this bolt also. And after that we calculate this Rn, which is one of those two equations, the smallest value, and we calculate phi Tn as phi Rn here, which is this the design strength for this connection to prevent the block shear failure. So let's have an example of this. So here we have this problem. For the shown steel shear block, considering if yield equals 50 ksi, if ultimate equals 65 ksi, bolt's diameter to be 7/8 inch, thickness of the web to be 3/8 inch, and assuming UBS equals 1, what is most nearly the maximum tensile load the connection can support? So in order to solve this, we will start first by calculating the areas which we have shown in our last slide, which are the gross area for shear, the net area for shear, and the net area for tension. The area gross for shear, it is going to be this length multiplied by the thickness, and this length is 1.5 plus 3 plus 3, so it is 7.5 multiplied by the thickness, which is 3 over 8, so it is going to be 2.81 inches square. After that, we will calculate the area for shear net, which is going to be 2.81, which is the gross area, minus the area for the bolts. And the area for the bolts, it is 7 over 8, which is the diameter of each bolt, plus 1 over 16, which is for the tolerance, plus 1 over 16 again, which is for to compensate for any damage. So it is 7 over 8 plus 1 over 16 plus 1 over 16. This is for each bolt. Multiply by 2.5 because we have a full bolt, and half bolt. So it is multiplied by 2.5 multiplied by 3 over 8, which is the thickness of the web. So the area net for shear, it is going to be 1.87 inches square. After that, we will calculate the area net for tension, which is this area here. So it is going to be 1.5, which is this height, multiplied by 3.3 over 8, which is the thickness of the web, minus 7 over 8, which is the diameter of the bolt, plus 1 over 16 plus 1 over 16, as we explained here, all multiplied by 0.5, which is because this is half bolt only, all multiplied by 3 over 8, which is the thickness of the web. All of this is going to be 0.37 inches square. So now we have all of the areas. We will just substitute in the first equation, which is phi Tn. It is going to be, we'll use phi here as 0.75 because this is for shear, multiplied by F ultimate, multiplied by this term here. All of the data, we have it now. We have the net area for the shear, we have for the tension, we have the area gross for the shear. So solving this equation, we will get 61.9 kips square. Solving for the second equation also, we will get phi Tn equals 63.75. So we will use always the smallest value, which is 61.9. So this is our answer here, which is 62 kips. So this is it for our video today. See you in our next video. Thank you.